Right, welcome back. In this unit, we'll talk about when is a function a total function or when is it only partial. Total versus partial refers to on the inputs. So now we're zooming in on the domain here. And the question is the function defined for every single input in the domain? Okay, so here let's kind of come at it from a different angle and define together the domain of definition of a function. Okay, so suppose I start with a function f from a to b. Recall a is the domain. The domain of definition of f, okay, is going to be potentially a subset of a that will contain those, the set of those elements on which f is actually defined. Okay, so in set builder notation, this is the collection of all little a in a, such that there exists some output value b in b, for which a comma b is in f. Okay, and here this notation a comma b in f, we'll see a little bit more about that later, but this just means that f of a is equal to b. So here's an example of a function. I've got my domain a, my codomain b, and some arrows. And let's check together, this really is a function because it's the case that for each input in a, I have at most one arrow coming out of it. Okay, this is not a proof, it's not formal, but this is visually how you can see that. And this is where the at most part comes into play. Note that here there's an element b that doesn't have any arrow coming out of it. And what does that mean? That means that f is simply not defined on the element b. That if I plug in b, I don't get any valid output. Okay, so what does that mean? Now putting this together, that means that for this function, the domain of definition is a strict subset of capital A, which includes only A, C, and D. Okay, so let's see some examples here. So one example, say for example, I'm going from f from reals to reals by f of x equals 1 over x. What is the domain of definition of this function? So note that this looks at first glance is a perfectly reasonable, perfectly good function, and it is, but it is not defined on all points because it is not defined on the point 0. Okay, so the domain of definition would be the set of real numbers with 0 removed. How about the function from n to q of f of x equals 1 over x? What do you think? It's a very similar thing. Exactly the same problem is that 1 over x is not defined for x equals 0. And remember that in this class, the natural numbers does contain 0. So here the domain of definition is n with 0 removed. Okay, now let's think a little bit more. How about the function from the natural numbers to reals defined by f of x equals x divided by pi? Okay, when does this function potentially break down? It doesn't. Okay, we'll have some other ones in other directions where it does. And watch out here. So this direction is perfectly fine because if I start with an integer, I divide it by pi, I get a real number. But for example, if my codomain instead of the reals were the natural numbers, then in fact this function is not well defined on any input value. Because if I take a natural number and divide it by pi, I will get something that is not a natural number. Okay, and if I've stated that my codomain would be n instead of r, then that's not a valid output value. Okay, so we'll see some examples of that form. But another example of kind of similar to some of the previous maybe, but to give you a flavor of these binary functions. So say I have f from r cross r to r, defined by f of xy equals 1 over x minus y. So what is the domain of definition here? Again, watch out because I'm dividing by something. I need to make sure I'm not dividing by 0. Okay, but earlier we were removing a single point when one input was 0. Here, what do I need to do? I need to remove an entire line, okay, of all the points where x is equal to y. So this leaves me with the remaining points, with the domain of definition is all the x comma y such that x is not equal to y. In this case, I will avoid division by 0. Okay, so this was the domain of definition of a function. And now we're ready to define when is a function total. Okay, and this is the case. A function is a total function if its domain of definition is equal to its domain. That is, it's defined, it's well defined on every single input value in the domain. Okay, so here in formal notation, this is equivalent to saying that for every A in big A, there exists a B in big B such that f of A is equal to B. That is, that for every input, there exists some output for that input. Okay, so some examples. As we saw, this one from the previous slide, the domain of definition was equal to the full domain N. Another example, say I'm going from natural numbers to natural numbers, f of x is equal to 2x. For any natural number, 2x is also a natural number. Okay, this one looks a little trickier. Let's see. How about, so f maps from n cross n without 0 to q by f of xy equals x over y. Why is this total? Is it defined on all points? And indeed, you can see the only place where this would not be defined is if y is equal to 0. But this is now not part of the domain. My domain that I started with was already n cross n without 0. Okay, so what does that mean? That means my second input, my y's, are not allowed to be 0. Okay, so graphically, what does being total look like? Well, it looks exactly like this. Okay, so on the left hand, I have an example of a function that's non-total, and on the right, there's a function that is total. And being total exactly means that out of every element in the domain A, you have exactly one arrow coming out of it. Okay, so why I have at least one because I'm total, and I have at most one because I need to be a function, so I can't have more than one arrow coming out. Okay, and over here on the total side, this domain of definition is equal to the entire domain. All right, so one point to note in terms of terminology, I've defined for you what is total, and now seemingly the opposite is partial. Okay, but actually, so how does it work? The idea is that every function is partial. Okay, so partial functions include both the total functions and the ones that are non-total. Okay, so you can never say this function is not partial. It's always partial. It's just that total ones are a special case of partial functions. Okay, so that is a partial function may, but does not have to, be defined on the entire domain. So, an important question that comes up a lot, in this class, or maybe even in general, if you see the word function, does it mean partial or does it mean total? The answer is unfortunately maybe not so satisfying, that it depends. It depends exactly what the context is. Some textbooks will use one convention, another textbook will use a different convention. So just kind of be aware of that, I'd say. And the literature in general is not consistent. For the purposes of this course, unless we otherwise specify or we ask you something specific about are these things total or not total, then the default is that we are talking about total functions. Okay, but if you're ever really in doubt, especially in an exam, you can feel free to ask. Okay, so this concludes the unit about partial versus total functions.